Hi, this short video explains different solutions with different time complexities for the maximum subsequence sum problem. Let me first briefly introduce this problem, and then after that introduction, I'm going to explain the three solutions that exist here in this Java project. So let's start by drawing a simple array of integers, and this is going to be a very short array because I just want to illustrate what the problem is. I don't want to do anything else. Let's say you have an array of 6 integers. The numbers are 4, 1, -20, 3, 7, and let's say 3. So here's the question. What is the maximum sum of subarrays in this given array? In other words, if you're allowed to pick any subarray in this array, as long as it is contiguous, means there's no holes in it, which subarray has the maximum sum of elements? For example, you can say, let's try some of the subarrays that exist in this array, like the subarray starts at 4, ending at -20. What's the sum of elements in this subarray? The answer is -15. Let's try a different one. The sum of elements in the subarray is starting from 1, ending at the first 3. The answer is -16. So far, -15 is the greatest one, right? But if you check this subarray, you will get to the maximum value. The maximum value or the maximum sum of the elements in this subarray starting from the first 3, ending at the second 3 would be 13, and that's basically the answer. That's the maximum sum of elements in any subarray in this given array, as long as the subarrays are contiguous. There's no hole in them, right? You cannot say, for example, I found a better solution. Let's pick 4 and 1, and then jump over -20, and then let's go over 3, 7, and 3. That's not the answer. That's not a good answer. Why? Because your chosen subsequence or the chosen subarray has a hole in it. You're jumping over -20 in order to reach to the maximum sum. That's not allowed. So the answer for this small given problem is 13. Now, this is a simple problem. This is a simple example. I'm going to solve this problem for the general case. If you want to pause the video right now and start thinking yourself, please do so, because in the next few minutes, I'm going to explain 3 separate solutions for these for this problem. I'm going to start with the most naive solution, or the brute force solution. Then I'm going to make it a little bit better, and then I'll show you at the end the optimal solution, which is the most complex one. All right, let's jump to the first solution. I stored this first solution in the cubic solution. The reason is the time complexity of this solution is going to be order of n cube. You'll see why, because there are like 3 nested for loops. In this solution, which is called the brute force solution, because there's no creativity in it, it's just checking the sum of all the subarrays possible in a given array. I have 3 for loops. First, I'm going to define a max sum, initialize it to 0, and at the end, I will return the max sum. Please note that if you have an array of all negative integers, the answer to the max subsequent sum problem is going to be 0, not any negative number. Why? Because if all the numbers are negative, your best solution, like the subarray with the maximum sum would be an empty subarray. And the sum of elements in an empty subarray is going to be equal to 0. So remember that very rarely, this very rare edge case. This is an edge case that, you know, rarely happen. But if you have all negative numbers, the answer is going to be 0. All right. I'm going to initialize max sum to 0, and I'm going to say the solution that we are looking for has a start index equal to solution start index, and a final index or end index equal to solution end index. We are going to figure out what these numbers are. I just initialize them to -1. That's just for the sake of initialization only. This is the main for loop of the solution. It looks for all subarrays starting at index start and ending at index end. So I need to have a for loop. The start subarray is going to be any number from 0 to the length of subarray, the length of array -1. The input array is A, so it's going to be A dot length -1. And I will have a start plus plus after every iteration of this. So in this outer for loop, I'm going to go over all the possible values for the start index. The next thing we can do, or we need to do, is to find out the end index. The end index cannot be smaller than the start index, so it should start at the start. So end minimum value is start, and its maximum value is again A dot length -1. And after every iteration of this inner for loop, we'll do end plus plus. So these two for loops combined will give you any combination of a start and end indices, where a start is less than or equal to end, and basically when you have a start and an end, you will have a subarray. The question is, which of these subarrays with the given start and end have the maximum sum of elements? In order to answer this question, I have created this code. This code is basically starts with defining or declaring a temporary sum, this sum initialized to 0, and then I will use a for loop to count or to add all elements in the given subarray from start to end. So for k from start, k less than or equal to n k plus plus, this sum plus equal a.k.a. Right? So this basically adds all the elements in the subarray that looks like this. It just starts with the start index and ends with the end index. After I find this sum, then I will see if it's greater than the max sum. If it is greater than max sum is the currently observed maximum element, maximum sum, right? As you go further in the algorithm, the max sum can change multiple times. If this sum is greater than max sum should be updated to this sum. And then we can store the solution so we can find out where exactly this subsequent exists. Where is the beginning of the subarray? Where is the end of the subarray? Whose sum is the maximum? So we say solution starts index is equal to start, solution end index is equal to end. After we finish this whole nested for loops, then we are going to print the following. Subsequence with the max sum is from index solution start index to index solution end index. And then we're going to return the max sum. That's the brute force n cube. That's a brute force n cube solution. Now let's make this a little bit better. I'm going to show you the quadratic solution. The quadratic solution basically means the time complexity is n squared, where n is the length of the array. This solution is almost identical to the cubic one with a very small difference. If you compare them side by side, this is the cubic one. This is the quadratic one. As you see, the first outer for loop is the same. The second for loop here is, setting n from a start to the a dot length. Same story here. So the two for loops are basically the same. The only difference is in the cubic solution, there was a third innermost for loop, but in the quadratic solution, I deleted it, and I kind of combined the for loop with counter k with the for loop with counter end. So the for loops, the second and third inner for loops, were combined into one. How's it possible? Let me explain that. So the outer for loop doesn't change. Then we have a temporary integer in this sum initialized to 0. In the cubic solution, we have defined this further down, but here I define it right here. And then right after that, I'm going to find out what the end will be. It's going to be anywhere from a start to the a dot length minus 1. And while I'm changing the value of end index, I will update this sum, right? So I don't find this sum in a separate for loop. While I'm like moving end away from the start index, I calculate this sum just to save time, right? And then I will say, if this sum is greater than max, update the max. This part is similar to what we did in the cubic solution. The only difference between this and the cubic one is that in this one, the third for loop, the innermost for loop is gone, and it's kind of combined with the second one. So at the end, you just print the answer, and that's it. So this one is quadratic. Why? Because you have two for loops, right? So it's going to be quadratic. The next step is finding out how we can do that quadratic solution better. It's not an easy way to do it. There's no easy way to do this to improve that. I find the quasilinear solution. Quasilinear means the time complexity is order of n log n, which is not easy to get. It's a little bit too complex for your level. It's good to see like interesting and complex algorithms, because you gradually learn how the complex algorithms are and how to come up with a complex algorithm yourself. But if you have a hard time understanding it, that's totally fine, because that's a hard algorithm to understand at this point, because it uses recursion and it is basically solving the problem in a divide and conquer fashion. So this is the answer. This is a public static int method called maximum subsequence sum that gets an array, and it calls a helper method. The helper method is a recursive function or recursive method that gets an array, gets the leftmost index and the rightmost index, which is going to be 0 and length minus 1, and returns the answer. Let's look at the body of max subsequence sum or max sum recursion. I'm sorry, max sum recursive. I call it max sum rec. It's a private static method. Why it's private? Because no one outside of this class is allowed to call it. This is only used within the public max subsequence sum, so we don't need to define it public. Private is good enough. And like any other recursive method, it starts with the base case. The base case is this: if your left and right indices are basically referring to the same number. If left is equal to right, you're basically calling this helper method to find the maximum subsequent sum of a subarray of length 1, because if left is equal to right, you're looking to find the answer for a subarray from left to right. So basically you have only one element in it. If you're looking for the answer for an array of size 1 or a subarray of size 1, then here is the answer. If the only element in this subarray is positive, you return that value. Otherwise, if it's 0 or negative, you will return 0. I told you before, if a subarray or an array is made of all negative numbers, the maximum subsequent sum is going to be 0. This is the base case, but what's going to be the recursive step? Let me explain the recursive step using a very simple diagram. I'm going to annotate with my favorite color, the light green. So imagine you have a long array, and this is my left index, and this is my right index. Then I will calculate the center, which is the average of left and right. This is going to be my center, which is calculated this way, line 16, left plus right minus left over 2. You may say, why don't you just say center equals left plus right over 2? The answer is given in the comment section. You can read it. The reason is when you write it this way, there's a chance of integer overflow. If left and right are big numbers, let's say in the order of billions, let's say left is 1.5, right is 2 billion. When you add them together, you are going to exceed the maximum possible value for integers, which is 2.15 billion. And you would end up with a negative number for your center. And this is going to cause an index out of bound exception for sure. So try to avoid left plus right over 2 when you're finding the average of two numbers left and right. And instead, you can use left plus right minus left over 2, which is going to reduce the chance of integer overflow to 0. Anyways, I broke this subarray into two pieces from left to center. I'm going to call the subarray from left to center the left one, and I'm going to call the other one the subarray from center plus 1 to right, the right subarray. So I have the left subarray and I have the right subarray. Right? Here is the logic of this solution. The answer, which is basically the subarray or subsequence with the maximum sum, can either be in the left subarray completely. So the answer can lie within the left subarray. Let's call this answer. That's case 1. Or it can lie completely within the right subarray. We call this answer number 2, or the answer in the second case. And there's a third case where the answer can straddle the border of left and right, which means the center index. So in the third case, the answer can be basically partly in the left subarray and partly in the right subarray. Everyone can agree on this. The answer can either be completely within the left subarray or within the right subarray, or it can be partly in the left and partly in the right. There's nothing wrong about this. This is basically pure logic. Everybody understand the pure logic of, where the answer is, right? So I'm going to use this simple discussion, simple logic, simple proposition, logical statement to solve this hard problem. Here is what I will do. I will say, let's first take care of case one. What is case one? When we use this. All right. What is case one? Case one is when the solution lies in the left half. So I use the what do you call this? The recursive call to the max sum rec to find the answer to the same problem if the answer lies in the left subarray. So how do I get how do I focus on the left subarray? I'm going to start with left and end at center. When I pass the left and center as a second and third parameter to the max sum rec, it only looks for the answer in the left subarray. That's going to give us the answer for the left or for case one, for the left half. I use the same function call, but this time instead of using left and center as the second and third parameters, I use center plus one and right. So I only pass the right subarray, the right half of my array, and this method is going to call this method is going to return the maximum right sum in a recursive fashion. So now I have the answer for case one, which is max left sum, the answer for case two, the max right sum. And now the only thing that I need to consider before I come up with the answer is what happens to the third case. What's the best solution that satisfies case three limitation, which was a subsequence that start in the left half and end in the right half, right? To answer that, we need to basically use two for loops. The first for loop finds the maximum sum of subarray ending at index center. So the first for loop assumes that the answer starts somewhere here. We don't know exactly where, but somewhere within the left subarray, between left and center, and ends at the center. I call this max left border sum. This is basically the same name that is given by the textbook. You can check out the textbook's explanation as well. So basically, what I do is I first find the max left border sum, which means starting at anywhere in the left subarray, ending at center. And let's use this assumption to find the max left border sum. All I need to do is I need to have a for loop, I from center, I greater than left, I minus minus, and I gradually move I away from center, go to the left. And each time I add left border sum, which was initialized to 0 by a plus I. If left border sum at any point is greater than max left border sum, update the max left border sum and set it equal to left border sum. Right? This is going to give me the best subarray, or the subarray starting at any point in the left subarray and ending at center with the maximum sum. After taking care of this, we are going to exceed to the next for loop in the same third case. The next for loop basically says, let's find the maximum right border sum, which means the sum of elements in a subarray whose start index is going to be center plus one. So right, it starts right here and ends somewhere within the right subarray, and its sum is the maximum. So it basically uses a similar for loop. It starts I from center plus one all the way to right. In each iteration, it does I plus plus. right border sum, which is initialized to 0, it's always added by AI. If the right border sum exceeds the maximum right border sum, updates the maximum right border sum. By the end of this for loop, the max right border sum will be the maximum we are looking for. Now, in order to find out the case 3 answers, what we need to do is we need to add the maximum left border sum, which is calculated within this for loop, by maximum right border sum, which is calculated in the next for loop. So basically, this is the answer. And that's going to be the case 3 solution, right? So the final answer would be the maximum number that we get in case 1, max left sum, case 2, max right sum, and case 3, which was max left border sum plus max right border sum. We have to do case 3 in 2 separate for loops because, you know, it straddles the border, so you need to calculate half of the solution in the left subarray and half the other half in the right subarray. So that's why I needed like 2 for loops. After you take care of that, you know, after you get the maximum, that would be the answer. And what is the max 3? Max 3 is a private static integer method that gets 3 integers and returns the maximum. You can check out the logic. The logic is using only 2 comparisons to find the maximum of 3 elements. It's an efficient algorithm, which I'll explain more about this when we talk about sorting algorithms. So that's pretty much it. Hope you enjoyed the video. Thank you.